Alright, homework 12, problem 2. So in homework 12, the problem 2, we are given an input x of t, which is composed of f of t plus a white noise WSS signal. And this, you get an output, so for x of t we get the output y of t. Now, because the convolution is linear, if I put this through the system, it's really just going to be as if I put this through the system and then add this and put it through the system. So the output, if I just put this through the system, will just be yf of t, and the output, if I just put this through the system, will be yn of t. And then the sum of them together gives me the sum of these two together at the input. So the problem wants us to find h of t, the impulse response, such that the output is such that it maximizes the output signal to noise ratio. So some things to note. N of t is WSS white noise. So that means that its expected value is 0. Also, they tell us that it has unit spectral density. So what does that mean? It means that S of omega is equal to 1. And recall that the spectral density is the Fourier transform of the autocorrelation. In this case, because it's a WSS, we can write tau because it's the time difference. Okay, signal to noise ratio is defined as such. So to find signal to noise ratio, we need to find this piece and divide it by the expected value of y of n squared, and take the square root and take the ratio and then maximize it. Okay, so let's find yf of t. So yf of, I'm going to put it at t naught, is equal to, it's just the convolution of this guy with the system. So we have, with the impulse response of the system. So we have this, just standard convolution. Now, convolution in the time domain is the same thing as multiplication in the frequency domain. So, because right now we're in the time domain, in the frequency domain, if I take capital F and capital H, I can multiply them together and I get the same value. However, we want to make sure that we stay in the time domain because we want yf of t. So, in order to stay in the time domain, right, we can still do this multiplication. However, we have to, right, because this in the time domain is the same as the multiplication of this in the frequency, but we want to stay in the time domain. So to take this and bring it back into the time domain, we take the inverse Fourier transform, and then we're good because now we're still in the time domain. So then it's basically just rewriting what I have here. So we have found the first piece right here. Now we've got to find the bottom, which is a little harder. So what is this equal to? Its expected value of yn of t naught, yn of t naught, which is equal to the autocorrelation of yn of 0. We know that because when we put in n of t, right? So yn of t is a WSS because we proved in problem 1 that when we put a WSS signal through a system, we get the output to be WSS. So we know that the autocorrelation will just be a function of the time difference. That's why we can write that. Okay. Okay, so using what we have here, we can write r yn of tau, the time difference, as, because the autocorrelation, the Fourier transform of the autocorrelation is S, we can say that the inverse Fourier transform of this is equal to the autocorrelation. So I take the inverse Fourier transform, because we're doing yn, it's s of yn of omega, e to the j omega tau d omega. But s of yn, we can write it as s omega times absolute value of h of omega squared, e to the j omega tau d omega. Now remember that we're evaluating this at tau equals 0. So the the tau goes to 0, so this goes to 1. So we're left with this, s omega d omega. But we know that because n of t is unit spectral density, this guy just becomes 1. So we're just left with, we are just left with this. By the way, the limits here are the same, I just got lazy. We have this. And this is equal to this, so we have the second piece. Now we just have to take the ratio of the two. So, rho, which is the signal to noise ratio, is equal to, so we have yf of t naught, absolute value. So we have 1 over 2 pi integral, I'm going to put the absolute value soon, 1 second. Omega t naught, d omega, absolute value, over, I wanted to, this is the problem because I write really big, so I don't want you to think that I'm saying that rho is the top. Rho is this. Okay, so then we have the bottom, the square root of the bottom. So we have square root 1 over 2 pi so we have this. This is the signal to noise ratio, but we want to maximize this. So it turns out that we can use the Schwartz inequality to maximize this. So the Schwartz, so I'll write it. So we have, basically to use the Schwartz inequality, we need to get this guy squared. So what the numerator squared. So let's just square everything. So we get, I'm going to write this guy last because I want to make it absolutely clear. So we want to square the top. Squared. This is equal to rho squared. We square the bottom, we get rid of the absolute, the square root. Okay, I don't know if I'll be able to fit this, I'll do my best. So, the Schwartz inequality says that the absolute value of this whole thing up here squared, by the way, the denominator stays the same because this is like a factor that we're scaling by, so we have to keep that in on the other side here. The Schwartz inequality calls, let me be careful here. So let's say because it's a multiplication, I can move them around. I want to call this piece, I'm going to call this piece G, and then this piece I call F. So I'm just going to write it over here, it's a little easier. Let me make sure I write the right thing. This is I'm just writing the Schwartz inequality just to have it so that it's absolutely clear what I'm doing. So the Schwarz inequality says that the absolute value squared of an integral where you have two functions multiplying each other is less than or equal to the integral of one of the functions absolute value squared in the integral times the other function absolute value squared in the integral. So we're going to do the same thing here on the top. All right, so I'm going to call this piece that I circled in red, I'm going to call that I'm going to call that the g of x, and the other one I'm going to call the f of x. I mean, it's not of x, it's of omega, but you get the idea. So we have on the top, we get this guy because it's just a constant squared. Then we have f of omega. I'm trying to fit all this here. I hope I can fit it. Squared. And then we have h of omega, absolute value squared, d omega. And these limits are still from minus infinity to infinity. So, what's great here, cancel this with this, and cancel this with this. So, this is maximized if and only if, and using this example, so this is maximized if and only if f of x is equal to k g conjugate of x. So this is maximized only if, so we have f of x, which we called h of omega, is equal to some constant k times g conjugate. So it would be f conjugate times e to the minus j omega t naught. So let's do the inverse Fourier transform of both sides. So we get h of t. This is a constant which comes out. We have 1 over 2 pi integral of this e to the minus j omega t naught, e to the j omega t d omega minus infinity to infinity. Okay, so we can write f star of omega e to the minus j omega t naught minus t d omega. Okay, I'm going to now take the conjugate of both sides, so I get h star of t equals k 1 over 2 pi. Here I get f of omega e to the j omega t naught minus t d omega. And this is the same as you take the inverse transform of this, you get f t naught minus t. These are still minus infinity to infinity. And then I take the conjugate again of both sides, and I get h of t is equal to k f star t naught minus t. So this constant k doesn't really matter in our case because we can cancel these two pieces out, right? And h of omega has this k, but it doesn't matter because they get rid of them. So, and k can be anything, so we have h of t. So this is maximized, the signal to noise ratio is maximized when this is true. Now we have another piece to the problem where they say plot the filter response h of t when the input f of t is a rectangular pulse of duration capital T. Okay, so we can now, if f of t is real, right, then h of t just equals f of t naught minus t, because the conjugate of a real function is just the function itself. So part A asks, what does this look like if t naught equals t? So just for starters, f of t is a rectangular pulse of length t. So this is f of t. Now we have here they want us to plot f of capital T minus t. So minus t would mean to take this guy and flip it over, and then we're adding t, so that would mean we would shift it to the right by t. So basically, in this case, we get exactly the same thing back. This is for part A. Because we flip it over and shift it by t, and we get the same thing back. Now they say b is t naught is equal to capital T over 2. So we have h of t is equal to f of t over 2 minus t. So similar principle, we flip this over, but now we shift it only by t over 2. So we get something like this. Minus t over 2. And then for 2t, see if I can fit it here. Hopefully I can. So t naught equals 2t. We have h of t equals f of 2t minus t. So again, same principle. We flip it over, but now we're shifting it to the right by 2t. So if this was t, right, we shift by t, we get here. But then we shift by another t, so then we go here. And this point over here, which you can't see because I'm right on the margin, is 2t. And this point over here, in case you can't see, is t. So that's what this looks like. And that completes the problem.